Okay, I guess the point of this final video is to kind of wrap things up with, make you think about a few special cases to see if you're engaged with what's kind of going on. Here's a case, for example, where we'd have maybe a pivot here, so I'm going to have a load at A, a reaction at B, maybe another load at C, and another reaction at D. So we're going to have some loads here, 10 kilonewtons and 80 kilonewtons. Now this is an example perhaps where our usual rule of going to the leftmost pivot and taking that to be the location where you're going to take moments around, you might want to not actually use. That's an example, because if you went for the rightmost pivot, you've got the advantage that you're looking back at distances all the way at these these various forces to your left, although we normally like to look at things going off to the right. So when you come to the issue of what's going clockwise and anti-clockwise, the arrow in terms of the face of it going that the clock face is sort of coming up, going up in this direction, it's easier for you to then say, well, that one's going to be negative, that one's going to be positive, that one's going to be negative. Whereas if you took your pivot here, you've then got to remember, you're going around your clock face, that's going to be positive, but that's going to be negative, that's going to be negative. So you're mixing up various negative and positive ways of thinking as you're going through to do your problem. So this is an example where we might not want to take our moments at the leftmost pivot. The other alternative, of course, is we could take moments at the leftmost point on the beam. The disadvantage there is that we're then get an unknown from B and an unknown from D. We get a set of two simultaneous equations we would have to deal with, and that's not great either. So taking moments here is not great. Taking moment here has got issues. Taking moments here might be the best option and worth considering. Another case to consider is, what about if we had 1 meter here, 2 meters here, so we've got a load there, and then another 1 meter to this other pivot there. So we've got a scenario set up like this. So 1 meter, 2 meters here, and what I'm going to do, of course, is I'm going to apply 50 kilonewtons at this point, and surprise surprise, I'll put 100 kilonewtons at that point. Now can you see automatically what we're going to get there? Well, you can see that I'm going to get a negative moment of 100 there, and I'm going to get a positive moment of 100 there. So I automatically should have a good grasp that what's going to happen to this reaction. This reaction is balancing these two forces. So this pivot here, well, it's not going to do anything. So its reaction, when I work it out, I should expect to get a 0 reaction there. So it's not a crazy result when we're looking at a beam that we end up with a zero result, because we could end up with the forces all balancing and pushing down just on one pivot. Okay, so that's a possibility. If you're starting to get a negative reaction, well then either the person set you the question's done something wrong, or you've overlooked something. For instance, you could have a problem like, I don't know, let's go for a sort of similar sort of case. 1 meter, then we've got a pivot, 2 meters, then we've got a load, another meter, and then we've got another pivot. Okay, and in this case I'm gonna I'll double the load at the end, so we'll put 200 kilonewtons here. We'll keep the 50 kilonewtons here. So this case, when I work it out, I can see that I'm going to get a minus 100 moment around this point here, and I'm going to get 100 moment around this point here. What does that mean? Well, that means overall I'm going to get minus just 100, that's minus 200 at this point here. So overall I'm going to get a minus 100 kilonewton meters moment turning about this pivot here. What does that mean? Well, that means that this beam is either going to topple, it's going to spin off, or, well, you could say that I have to have a negative reaction at this point. Well, surely that's not possible. Well, it's not possible if your original diagram had a little kind of little pivot on wheels, or if it was a sharp pivot like that. So or some sort of design like that. So if this here was one of these things, then we know there's an error, or there's that might be deliberate, or we've misread something perhaps. However, if this pivot here on the original space diagram was a hinge, well then that would be a perfectly acceptable engineering case, and we would expect to get a negative reaction at this point here. So we're clamping down the beam at this point, we're putting a lot of weight on this point, and it's going to want to turn, but the hinge is going to stop it, and we'll end up with a negative reaction there on the right. Okay, so a negative reaction on a beam problem is possible if you kind of clamped it down with some sort of hinge device. What about a UDL? Okay, so in this case we'll have 1 meters here, 1 meters here, another meter here, like this, and then I'm going to have a UDL. Okay, over 2 meters. And my UDL will be 10 newtons per meter. Okay, can you see what the result is there? You should be able to see that you can do that problem without having to do any maths. I've got 2 meters worth of this UDL, so I'm going to have a total of 20 newtons. This UDL, it's a bit like if you could imagine a tightrope walker with a big heavy bar going across. So all the weight is going to push down on that pivot there, and again this pivot is going to end up with a zero reaction. So we're going to end up with the reaction at this point being 20 newtons. Okay, so even though you're expecting, maybe I should get a reaction there, we're not. Everything will be pushing down even though we've got this massless bar. So looking at a similar problem, what about if we had a similar sort of thing going on with, I've got one pivot here, one pivot here. I'm not going to put the distances there, but so that's my reaction 1. Reaction 2, I've got this massless bar, and I'm going to push down 10 kilonewtons there, and here I'm going to push down 30 kilonewtons there. Now you try putting some numbers in there and going through the process of taking moments and resolving forces, and surprise surprise, what do you think the result's going to be? The result is going to be that reaction 1 equals 10 kilonewtons, reaction 2 equals 30 kilonewtons, and it's almost as if the bar is not there at all. Okay, so again, think about, well, forces, how they're going to push down. They're going to want to push down to the most closest pivot that they can find, just although the fact that there's this bar in between ain't going to affect matters. It's just going to push down, and that's going to react by the same amount that's pushing down on it. And here, same case. Now you can go for the maths, put some distances in and try it yourself and prove it to yourself. Actually, you can solve it mathematically. So these were just some not actually solutions, but some things to make you think and engage your brain when you're trying to solve the problems, so well, so that you kind of have a sort of sanity check on your answers.